people that are on retreat that have requested that report. All right. So yesterday we were talking about field lines. Okay. Okay. So if we were talking about field lines, so when you have a single point charge, it's simple. It's easy. Okay. A simple, you just draw the little things that are coming in, you draw the little things that are going out. Why that's closed, I don't know. Okay, that's relatively easy to do. But when we talk about 2-point charges, it gets a little tricky. Now, yesterday we talked about if you have two oppositely charged things. Now, as long as the test particle is on our other side, the same basic rules apply. If they're pluses, it pushes away. If they're negatives, they pull in, as long as the test particle is the same charge. But let's say we had our point charges that look like this. Okay? If we had point charges that look like this and we wanted to test it out, okay, we'd use the same test particle, the common test particle, so our little baby proton. So if I take my little baby proton and I throw it at the positive test particle, what's it going to do? How's it going to move? Away. Away, right? It's going to get pushed away. If I did it from the top, how would it get moved? Up and away, right? From the bottom, down and away. And likewise, anywhere, it gets pushed away. Everybody follow that? Yes? Now, let's say I took my little test particle, put it on the other side. I'm going to throw that little red test particle at the negative point charge. What's going to happen? It's going to move towards, it's going to get pulled in. Anywhere on this side, it's going to get pulled in. Cool? The issue we run into, or the place where it gets a little wacky, let's say I put it there. If I put my test particle there, in between the two, what's the positive point charge going to want to do to that little red ball? Repel. It's going to want to repel it. It's going to push it, push it, push it, push it, push it, push it, push it. Now, once you get to about halfway between the two particles, who's going to start now taking more of an effect? The negative. And what's the negative going to do? Pull it. It's going to pull it in. And so what you're going to get is a field line that looks like this. Does that make sense? Okay? And if I move that little point particle a little bit up, right? Well, what would happen is the same thing. It would go like this, but then the closer you get to the middle, the less the negative would, the less the positive would have, and the more the negative. And so the line, instead of going in a nice straight line, would actually start to curve. And what you would end up with is that. Same thing here. Like that. So this is the field that you would end up with if you had oppositely charged point charges. Does that make sense? And obviously there are an innumerable number of little lines that I could put in between, but I just did these three so you guys get an idea. Okay? So if you get asked to draw field lines, one of the important things when you get these types of questions is please read the question, because every time I give one of these questions it says draw a minimum of 4 lines and somebody draws 1 or 2. And if you do that, guess what? The question has to get marked wrong because you didn't follow the same basic direction. You could have done them the right way, you could have put them in the right direction, but you have got to write them down right. That's what you see. Okay, let's look. Make sure you don't need to sit in front. All right. So please make sure you follow directions. Second, it's going to ask you to include arrows. Make sure you include arrows. Now for these, it's easy. If you want to, for the ones that are on the outside, that's perfectly fine. For the ones that are in the middle, if you wanted to include like an arrow here, here, and here, and then the blue ones on the other side, you would be fine in doing that as well. So does that make sense? Yes? Yeah? So we figured out what it looks like if you're talking about a point particle around a single positive, a single negative, oppositely charged point, and like point. There is one other one that you need to look at, and it's going to play a role in what we start talking about. And that is the field. Oh, let's use a different color. Between parallel plates. Okay, this is a term that you're going to see. I want you to be able to visualize what we're talking about. So when we talk about parallel plates, what are we talking about? Okay, we're literally talking about you take one hunk of metal and orient it parallel to another big hunk of metal usually, or some sort of conductor, but usually they're metal. And each one of those you're going to connect to a terminal. One of those is going to get positive, and usually one of them is going to get negative. Let's say this one is going to be a positively charged plate. And this one's going to be a negatively charged plate. Okay? If I was to take a test particle, a little positively charged test particle, we'll say, a proton, and I was to chuck it right there, in between the two of them. So I literally just wheel up and just throw it in there. Okay? What's going to happen to that test particle? Which way is it going to get pushed or pulled? Down. Okay? It's going to get pushed. Straight down. Does that make sense? Yes? Now, it looks straight down. There's only one place between, or I should say two places between parallel plates where it's not straight down. And that's going to be right at the edges. The reason that they're nice and straight is because wherever there's a field line, there's another one right next to it. So remember our rule, what can't field lines do? Cross, right? So they keep themselves nice and straight. But when you get to the edge, you've got a little bit more wiggle room. And so what the field lines are going to do out here is they're just going to kind of curve. Like that. They're still going down, which is a little bit of a curve on the edge. Does that make sense? Yes? Okay.
Doesn't it get more complicated when the plate gets smaller and then we have
Yes, also the
the induction?
Yeah, also just
The rectangle.
yes, but we're not doing that yet. That's because you're talking about magnetism and all that stuff. Okay? Does everybody understand that? Yes? Now, so we figured out the way that the fields look. And that's one part of understanding field lines, right? When you did topographic maps or isomaps or isobars or all those things, you had to figure out the layout and what it looked like and how, how it looked like that tiered level and all that stuff. But the other important part was to know the number values, right? One of the questions you were asked when you did topographic maps was, which is the steeper side of the mountain? which is the gentler side of the mountain. When you did isotherms and isobars, where's the greatest pressure shift? Which way does the wind blow? All these things you learned in earth science, right? And how did you figure that out? Well, you figured it out by looking at the lines and seeing how close together they were, and that would tell you the steepness or the change in pressure or this, that, whatever. Well, when we look at electric field lines, we want to measure something very similar. We want to know how strong the field is. Okay? So we want to be able to measure the electric field strength. Okay? So we want to know how strong is the field. Okay? Now, that's pretty straightforward, pretty simple, okay? Easy enough if we're looking at it, right? If you have an electric field, you need to know how hard that test particle is getting tugged. The harder it's getting tugged, the stronger the field is. Simple enough? Yes? Now, the formula for it is really, really simple. Oh, this is killing me. Okay? If you look in your reference table, everybody pull your reference table out. Okay? If you look at the page that has the electric formulas on it, not a whole lot of them. Okay, I think it's page 4. Is it page 4 or page 5? 4. Page 4. Okay? You will see this formula. Does everybody see that formula? Okay? Now, in electricity, some of the letters are slightly different. They have slightly different meanings. In this case, okay, the E stands for electric field strength. So the strength of the field. The other two values you should easily recognize. What is FE?
Electrostatic force.
Electrostatic force. And Q? Charge. Now, specifically, it is the charge of the test particle. Okay? Now, we talked about the test particle yesterday. What is our most common test particle that we use when we're talking about electric fields? A proton. Okay? And what is the charge on a proton? Positive what? We're talking about a formula now. Okay? And we said when we talk about charge in a formula, what do we use?
A 1.6 times 10⁻⁴.
Coulomb. Yes? When we talk about charge in these formulas, when we start using Q, when we want the quantity of charge, that quantity of charge must be in coulombs. So this is in coulombs. Okay? Why do I say that? Because sometimes you'll get a question where I'll say you have one electron. Or your test particle in this case is a 4e positive. And you go and put that into the formula. You can't do that. Your Q cannot be in elementary particles. Your Q must be in coulombs. Okay? Now, what is your unit going to be for FE? Is it F? It's a force. What's 4 units of force? Square. Newton. So this is going to be Newton. And we said Q is going to be coulombs. So what is the unit for your electric field strength? That's right. We don't usually use that in Regents physics. Instead, we just use it on the board, which is newtons per coulomb. Okay, the unit for electric field strength is newtons per coulomb. Does that make sense? Yeah. So, how are we going to put this together? Simple. Good. This is a typical question that you get. Okay, so you have 2 point charges that are separated by a distance of 4.0 times 10 to the 9th meter. If each point charge has a value of 8.0 times 10 to the negative 19 coulombs, what is the field strength experienced by a test particle sitting between them? What do we do first?
Wait, that says 10 to the negative 19?
Yes. Sorry, my handwriting isn't great. What do we do first? Key, we always do a key. Does everybody have a question? Yes, are we good? Okay. Let's make our key. Yeah? What do we put down first? What do we know? We know Q. What's Q? Okay, what else do we know? Distance, okay? But we're talking about the distance between 2 point charges. Do we know if it's a straight line or a circle or this or that? So it's a radial distance, yes? So what letter do we use? Do we use D or do we use something else? R, right? What is it? Geo? Units? Spiro, what should the units have been for this top one? Because you didn't give it to me. Coulombs. Okay, do we know anything else? No, the constant. What's the value? What's the letter and the value of the constant? Units? Help them out. What's the units for the K? If only you had a piece of paper where it was written down.
But that'd be convenient.
Newtons times meter squared over coulomb squared. Thank you. Okay, so what am I going to do? Find FE. So we're going to find FE. Okay? And we're going to use FE to solve for what? For what? For E. For E. So we need E in there too. Okay, so you have FE. So you're going to use this Q and the FE equals that over Q? Yes? No. You are finding the field strength experienced by a test particle. What is the value for a test particle?
1.6 times 10.
1.6. This Q is the 2-point charges. So this question is saying you have 2-point charges sitting like this. Yes? A certain distance apart from each other. My question is, what does a test particle have? So how many Q's are involved in this question? 3 Q's. You only have 1 Q written up there. You got to be specific. This Q is Q what? Q1 and Q2. You have to be specific. The other Q value, which we could call Q3 or Q test or whatever you want to do to keep it simpler for you, must also be included. Which is what? Tim? What's the test particle Q?
Oh, 1.6 times 10 to the negative 19.
Units?
Coulombs.
Does everybody understand that? Yes? This is where mistakes happen. Okay? You have to pay attention. I said the 2-point charges had one value. Okay? And then I asked you about a test charge. So you have to pay attention to what the question is asking you. Most of you probably could figure this out math-wise like that. But if you read the question wrong, it's going to jump up your answer. It's going to jump up how you work. So the first thing we want to figure out is the electrostatic force. So we're going to use the electrostatic force formula, which is, I'll do the hard part, Fe equals. So you're going to do that formula. And then once you get the Fe, what formula are you going to use? E equals Fe over Q. So these are the 2 formulas that you're going to use. Has everybody got that? Yes? Okay, so the first one, what do we get for the electrostatic force? Hold on, I know you got it.
No, I have a question.
Oh.
For once. Could you combine 2 into K, Q1, Q2 over QR squared to get the E from the outset?
You could, but that's going to confuse most people.
Because that's what I think happened.
You're going to confuse most people. Just, most people do the one formula. The other thing is do the one formula, get the answer. If you made a mistake, I can give you partial. You don't, if you do this one big jumble and it's hard to track your mistake, you're going to lose one.
I'm saying you just added one more variable.
I think some people think that that's enough variables in the first formula to play with. Am I wrong? Okay, so you should be doing 8.0 times 10 to the negative 19 times 8.0 times 10 to the negative 19 divided by 4.0 times 10 to the negative 9 meters. And what must you make sure you do to that bottom number? Because if you don't do it to the bottom number, it's going to screw up your answer. Square it, yes. Okay, don't forget to square that bottom number. And you multiply that by the K value. Okay. This isn't a pre-existing question. I just came up with it out of my head. So let's see what we get. Okay, so what do we get for a force? 3.6 times 10 to the, do we agree? Are we all just waiting for me to give you the answer? Don't work, girl. Well, let's see. It's going to be negative 19 to negative 19 on top, so that's going to be to the negative 38. And 3.6 is fine, right? And then the bottom, it's going to be negative 19 squared, negative 9 squared, so negative 9 squared gives you 18. Yes? Right? So negative 38 minus negative 18 is going to give you 20 times 9, so you got the 10, so that sounds about right. So it should come out to about the negative 10. Yes? Did we all get to the negative 10? 3.6 times 10 to the negative 10? Yes? Yes? Yes. Okay. Right? Why? Because you were solving for force. So you should remember that too. Right? Are we all good? Cool. Now, what do you do with that number?
Divided by the other Q.
Divided by the other Q, so you're going to plug this in here. Oh, not this is what we're doing. I did it. Cool. What do you get?
Oh, yeah, okay.
What, did you check it both ways?
Yeah.
What do we get? Come on, that's not hard. Alex?
2.25 times negative 29.
Negative 29? You made a mistake with your exponents.
2.25 times 10 to the negative, times 10 to the 1, 2, 3, 4, 5, 6, 7, 9.
Okay, it should be 2.25 times 10 to the 9. Think about it this way. If you're doing this, it's negative 10, right? And when you divide exponents, you subtract. Yes? So it's negative 10 minus 19. Right? So negative 10 minus 19, so that's negative 10 plus 19. So what do you end up with an answer? Positive 9. You have to remember that. Remember I told you, if you don't enter it to the calculator right, it does that algorithm, it's going to give you the wrong exponential answer. If you give you the first part right, it's going to give you the wrong exponential answer. So remember the rules for subtracting exponents. Does that make sense? And what's the units? Newtons per coulomb. Okay? So that gives you how strong the field is for a particular test particle in this event. Now, you could get this question as a three-part question. Find the electrostatic force, find the field intensity, and then I could ask you to draw the field between those two. Right? And I said they're identical, which means they have the same charge, which means what would it look like? What would the lines look like? Would they be going into each other, or would they be bending away from each other? Which one would it look like?
Bending away.
Bending away, like the one we did at the end of class yesterday. Yes? The only thing I didn't tell you was whether they were positive or negative, but you could kind of sort of assume they were positive because I didn't put a sign there. But typically, I would have to put the positive sign to make you draw it, so you could say whether the arrows were going in or the arrows were going out. Does that make sense? Yes? For homework tonight, okay, in your review book, okay, you're going to be doing pages 116 to 120. Now, that sounds like a lot, but 116 has 2 questions on it. 118 has 3 questions on it. Okay? So you're going to be doing those pages. Okay? But the homework's not due till Thursday because you have last one. Okay? So I will post the images for those on your Google Classroom for those of you who don't have the review book. Okay? If you do have the review book, you can get started now. Okay? If you have any questions, you can ask me now. Yes, ma'am. Was that on the previous page, right? Ah, too far. Okay. Okay?
A Tesla is Newton's per coulomb times meter. If I look that up.
More like the field.
Or really, it's Newton's per ampere.
Ampere, yes. Not ampere.